So, uh, up until now in this class, we've been focused entirely on calculating stresses and strains. And, stresses and strains um, represent points in a material. And you can kind of think of that as telling you how concerned you are about failure beginning at that point. Uh, how concerned you are about failure starting at that point. Um, but also, when you're designing something, there are times when even if the individual points aren't gonna, you're not gonna have failure at the individual points. Um, Too much sort of macroscopic change in the position of the thing can be a problem. Um, so let's say there are times you also care about overall changes in a body's shape, um, angle, position, etc., stuff like that. Okay, so for example, if you had say this was a balcony, okay, balcony. Okay, so um, even if this balcony was not in danger of breaking at any point, um, it would be a problem if a person standing at the edge like this caused a deformation like that. Um, so even if it doesn't fail, this wouldn't be. Every time you went out on your balcony, your propane canisters would fall off into the parking lot and stuff. Um, and so that gets us to a new topic, um, beam deflection, not deflections, beam displacements. And so now we're not talking about something breaking at a single point. We're talking about the overall body being not useful just because of the shape the thing takes. Um, and we're going to think about beam displacements. And by a beam displacement, here's what I mean. So let's say that um, this is the original shape of the beam. And after the deformation, let's say it's in that position, and the displacement, you can think of this displacement u as, every material point has a vector that goes from where it was to start with to where it is at the end. So this is the beam displacement of one material point. You could draw this vector for each one of these points. And you can think of the total displacement as being equal to the displacement due to the tension compression plus the displacement due to the shear force and bending moment. We're just going to think of it in terms of the bending moment. Those are related to each other. Plus the beam displacement due to the torque. And this idea will also be used to solve statically indeterminate structures. Here's an illustration of statically indeterminate structures. If you have a structure like this, by some force P there, you can solve for the external loads on each member using just statics. So using statics alone. But okay, so now let's take that same structure apply that same force over here. But now let's say we also put a member like this. Well, that seems like actually a pretty reasonable thing to do from a practical perspective. If this member is really thin here, you can tell intuitively that this is going to sort of warp in, So if you don't want it to warp in like that, just put a little reinforcement there. But if you tried to solve this using statics, you'd see that using just statics, you couldn't come up with, you couldn't solve for the external loads in that body. So you can't find all the external loads here using statics alone. Okay, so one way to tell that is as far as like thinking about it in terms of a statics problem, each joint is a restriction on the motion of a point in some way. Every joint restricts motions at that point. You know, some joints restrict rotations and translation. Some only restrict translation along one axis. Some restrict all, you know, displacements in every direction. But all a joint does is restrict motion in some way at a point. And so if you could look at the restrictions caused by all these points and remove at least one of those restrictions, like for example, this joint says that that point can't move anywhere. Okay, well, let's say that we change this into something that still prevented translation that way, but it didn't prevent translation that way. We took away one restriction that that joint applies. This structure would still be stationary. It could still, and in fact, I mean, we know that there's a bunch of restrictions we could take away because we can take away this whole body and it still would be still according to statics, right? That means that these are all redundant in some way, okay? And that means you can't solve it using statics. You can't use statics to solve for redundant restrictions like that. So this is called statically determinate. This one is called statically indeterminate. And the unsatisfying thing about this is, like I said, if you were really building a structure like this might even be like your first thought about how to build it, you know, because the statics might not be concerned with the deformation of that point of the material, but in a lot of cases you would be, you know. And so, and you know that if you built something like that, it's not like there would be some kind of weird mathematical thing and the forces would jump around between all these indeterminate values. Like that's a very stable structure. And if you measured the loads, they would be very stable. They wouldn't change. And so there must be a way to calculate the external loads on a body like that. Okay. It turns out that the way to calculate the loads on something that's statically indeterminate is to go through all the statics, come up with a bunch of equations due to the statics. You won't have enough equations to solve for all the variables. And then for your constraint equations, you need more equations to solve for it. Apply the restrictions that you know based on the type of material that you have. And so our extra equations that are going to make this solvable are going to come from what we learn about those macroscopic deformations, those displacements. Okay, so like for example, we're going to say whatever displacement, so with all the loads that are happening, wherever this point is displaced according to those loads on this member, it's still connected to that point on this member, so those displacements have to equal each other. Okay, it's kind of like the constraint thing in dynamics. Yep. Oh yeah, it's the same idea. Yeah, we're going to say that, so we're going to use the calculations that we can make about the displacements that come from loading to say that however those things deform, they have to agree where the joint is, and those will give us our extra equations. Okay. That was like a lot of just talking and like, but here's the simple idea. Okay, we're going to come up with ways to calculate the displacements at different points due to tension, bending moment, and torque. Okay, We're going to come up with formulas for that so we can calculate the displacements for a given load. Okay. And then once we can do that, we can apply it to multiple members that are supposed to meet in a single point and say that those displacements have to agree with each other. And that'll give us the extra equations that we need to solve statically indeterminate problems. Okay. So all through statics, you did all these complicated things. You did things that looked a lot more complicated than this, but you couldn't have solved this doing statics. But that's what we're going to finally, for the first time, be able to solve. Okay. So I'm going to go in order. This is sort of like the roadmap of what I'm going to do. I'm going to first go tension compression. And I'm going to talk about calculating the displacement. And then we're going to do statically indeterminate structures for members in tension and compression. This is also going to include thermal expansion, by the way. I'm going to fit it in somewhere. Then I'm going to talk about displacement due to bending moment. So we'll talk about deflection. And then we'll do statically indeterminate structures related to that. And then we'll do torque. The displacement that we're going to deal with is angle of twist. And then we'll talk about statically indeterminate structures. Okay, so for tension, compression, and thermal expansion, the displacement type is called elongation or contraction. All the other ones I gave the names for. So we're going to talk about elongation and contraction, then we're going to talk about deflection, then we're going to talk about angle of twist. Okay, any questions about what we're doing? Okay, so first I'm going to start with tension, compression, and so let's say that we have a section of beam where the internal load at every point in this along this beam is positive T. Okay, for the internal tension to be positive T, we'd have to have external load like this. And we'll use the coordinate system that we've used for beams this whole time. then the internal tension is positive T. The stress at every point is T over the cross-sectional area. Hooke's law says if you multiply out the appropriate part of the compliance matrix for the stress tensor, it says that if that's the only non-zero value of stress in the stress tensor, then the X normal strain is equal to 1 over E times the stress. And we can substitute in for the stress, and we get T over EA. And now if we think of every X value, so now think of the infinitesimal deformation or elongation at each X value. Okay, so imagine this piece being infinitesimal. That piece has a thickness of dx. The change in length of that piece of that disk in the X direction is du, and that's equal to the strain that we just calculated times that distance dx. So that's equal to exx dx, or P over EA dx. And so the elongation of the entire beam U is equal to the integral from 0 to the length of the beam of T dx over EA. That's the integral definition of the elongation. This is going to be more common for us if you can break the beam up into finite pieces with constant values of T, E, and A, then you can use a sum formula instead of the integral, and you get that the displacement is equal to the sum over all those finite pieces from 1 to n for n pieces of Ti Li over Ei. Okay, so let me do an example. Anybody have any questions yet? Okay. So let's say we have a pole kind of thing, and there's a 10,000 Newton force applied at the top and a 3,000 Newton force applied that way. And let's say over the whole pole, we have the same material. So Young's modulus for the whole thing, I guess we're saying this is steel, is 200 times 10 to the 9th pascals. And the area, cross-sectional area, is 0.01 meters squared. What's the displacement of the top of the pole? Let's see, we need to know some lengths here. So let's say that this is 1 meter and this is 1 meter. And basically we want to know when you apply this load from its resting length, is the pole going to get longer and by how much, or is it going to get shorter and by how much? We could also figure out like where this load is applied, would that be higher or lower? Okay, so that's the kind of question we want to ask. You can imagine an engineering setting where like it's not just a matter of whether you're worried about any of these points breaking. It's also that there's not very much clearance between the top and something above it or whatever, and you need to calculate, is this thing still going to all fit together when this displacement occurs? Okay. Well, first we have to calculate the external loads. Since we're used to dealing with tension compression along the x-axis, I'm going to reorient this. So I'm going to think of this as my x-axis, this is my y-axis, and I'm going to draw it that way. So now the 10,000 Newton force is applied at what I'm calling the right end, the way I've reoriented it. So which way is that 10,000 Newton force acting, left or right? Left. So we have 10,000 that way. And at the midpoint, we have 3,000 this way. And the first thing we have to do is calculate the, um, the load in the same line as these that's applied by the reaction. So I'll call that R. We're going to figure out what that R is. Now, in the second law, the only thing that we need to look at right now is the X component. Nothing's happening in Y, nothing's causing any moments or anything. So I'm going to just write this as R plus 3,000 minus 10,000 is equal to 0. So R is equal to positive 7,000 newtons. And so a free body diagram of the whole thing looks like this. We have the 7,000, the 3,000, and the 10,000. And now we want to calculate the internal loads on those two pieces, right? There's two cuts we have to make because there's three of these points where the subfunctions could change. So I'm going to do one cut where the right end of my isolated piece is between this and this. And then I'm going to do another cut where my isolated right end is between this and this. Okay. This is like, if you think of it this way now, it's just a super simple internal loads problem. You know, the only reason it doesn't look that familiar is because it's so much simpler than anything we've done, you know, but all we're doing is calculating the internal tensions. Okay, so cut one is going to be for X values between 0 and 1. We have the 7,000 Newton force. We haven't gotten to the 3,000. And so the only other force is the internal tension. And so the X component of Newton's second law says 7,000 plus T is equal to 0. So the internal tension for that piece is negative 7,000. And I skipped all the other stuff, but we would just see that the shear force is 0, the bending moment is 0, the force is 0. And now we'll do cut 2. This is for X values between 1 and 2. So this time we have the 7,000 on the left end. We also have the 3,000 going this way. And we have the internal tension. And the X component of the second law says positive 7,000 plus 3,000 plus T is equal to 0. So T is equal to negative 10,000. Okay, well, the elongation is going to be equal to the elongation on the first half, call it piece 1, plus the elongation on piece 2. We can break this up into two pieces. We figured out now that, so if this is piece 1, okay, the internal tension, the cross-sectional area, and the Young's modulus are all constant all the way from here to here. Okay, so that's piece 1. Figure out the elongation for that piece, and then we go to this one. On this piece, the internal tension, cross-sectional area, Young's modulus is constant. And so we'll just use the formula, the sum formula. And we get that the total elongation is equal to the internal tension on the first piece times the length of the first piece divided by the cross-sectional area and also divided by Young's modulus. And then we'll add that to the elongation from the second piece. The internal tension for that whole piece is negative 10,000. The length of the second piece is 1 meter. Cross-sectional area is 0.01. Young's modulus is 200 times 10 to the 9. And we get a total elongation of negative 8.5 times 10 to the minus 6 meters.
Beam, like a wall,
Mhm.
and a lot of them are tapered upward.
Mhm.
Could you just have like you would have the denominator would be different because the cross-sectional area is
Right.
different. Could you find a common denominator and get close enough?
Well, if it's continuously tapered, then you need to come up with a function. The area is a function of x and just integrate. Well, you'd integrate over the whole length. So let's do a problem like that. Okay, notice before we go on that that negative sign says that the beam. Ooh, that's actually the next example I have here. Okay, so the next example. So let's say that we have a beam like this. Let's say it's in tension with a magnitude of 20,000 newtons each end. Let's say the whole thing has a length of half a meter. And let's say the cross section is square the whole time. And let's say it starts out with side lengths of 1 centimeter. And when you get to the other end, it's side lengths of 6 centimeters. What's the elongation? How many cuts do you need to do for this one? One. What's the internal load going to be on that cut? What's the internal tension going to be? Positive. It's in tension. Um, so T is equal to negative 20,000 over the whole thing. Nope. That's what I just said. Yeah. Positive 20,000. It's in tension. And now we need to come up with the width of one of those sides as a function of x. Okay? Like, I mean, basically, what we really need in the end is the cross-sectional area as a function of x. Okay? But that's going to be equal to, you can think of it as the width as a function of x squared. Well, if you think of a graph of the width as a function of x, it's going to start at 1 centimeter. When x is equal to 0, and when x is equal to 0.5, it's going to be at 6 centimeters. And it's a linear function. So y equals mx plus b. B is 0.01, that's the y-intercept. The slope is a rise of 0.06 meters minus 0.01 meters divided by a run of 0.5. So you have 0.10. And so W as a function of x is 0.10x plus 0.01 for m, 0.05 over 0.5. And so now the area as a function of x is 0.1x, the quantity 0.1x plus 0.01 squared. So that's 0.01x squared plus 0.002x plus 1 times 10 to the minus 4. I think that's right. And so now the elongation, you can write it as u, or I think a lot of times I also write it as delta, is the integral for x from 0 to 0.5 of the internal tension dx over E. I'm going to assume this is steel again, times the cross-sectional area. I guess I'll put this back in the form 0.10x plus 0.01 quantity squared. And just to simplify this, let's multiply. You can think of this as two separate, we have two of these terms, 0.10x plus 0.01. Multiply both of them by 10. So if you multiply the denominator by 10 times 10, 100, you have to multiply the numerator by 100. So we have 0 to 0.5 of 2 times 10 to the 6 dx over 200 times 10 to the 9 times the quantity x plus 0.1 squared. And we can simplify a little more. We have the 2, so 2 times 10 to the 6 over 2 times 10 to the 11. So that's 2 times 10 to the minus 5 pulled outside of this integral. Of dx over the quantity x plus 0.1 squared. Notice by the time we wrote this integral down, like we were done with the concept. Now we're just like integrating this thing that's sort of ugly because that function is in the denominator. But well, I was just going to go use substitution. So I'm going to make u equal to x plus 0.1, then du dx is equal to 1. So dx is equal to du. And so this integral is 2 times 10 to the minus 5. The boundaries now are 0.1 to 0.6. And the integral is du over u squared. And so that's 2 times 10 to the minus 5 times negative u to the minus 1. Evaluated from 0.1 to 0.6. Oh, those 2's canceled a while ago. What do I have here? This should have, where I pulled this outside, this should have just been 1 times 10 to the minus 5. Still working on my division. 1 times 10 to the minus 5. That's a 1. That's a 1. And when you punch that all in, you get that the elongation is 8.3 repeating times 10 to the minus 5 meters, or 83.3 repeating microns. So yeah, that's what you have to do if you have a continuously changing cross section. No, right, because of the continuity, yeah. Okay, any questions? All right, that's all for today.